see if this works again. Okay. Maximum money robot can earn. I can stem this. We're starting a new streak here. Medium. You're given an n by n grid. A robot starts at the top left corner of the grid, 0, 0, and wants to reach the bottom right corner, m minus 1, n minus 1. The robot can move either right, left, right, or down at any point in time. The grid contains values coin at ij in each cell. If coins at ij is greater than or equal to 0, the robot gains that many coins. If it's less than 0, the robot encounters the robber. The robber steals the absolute value of coins at ij. Okay, so it's just deducting that amount. Okay. What if the person doesn't have that much? Okay. The robot has a special ability to neutralize robbers in at most 2 cells in its path, preventing them from stealing coins in those cells. The robot's total coins can be negative. Okay. That answers my question. Return the maximum profit the robber can gain on the route. Can the answer end up being negative, I guess? Probably, right? If all the cells are kind of negative and only 2 gets zeroed out, right? Probably a negative possible answer. Okay. This looks like dynamic programming, where where you kind of iterate over all the cells and come up with the highest amount of coins to get to that cell for every possible number of kind of uses of the zero out special property. So here I'm going to say this is dynamic programming. In dynamic programming, I generally think of states, and the states would be kind of transitioned, right? Like it's almost like a, what is it called? Like a Turing computer? Turing diagram? Turing machine. Yeah, a Turing machine. The states being, in this case, row, column, and number of uses of special. Basically, they're your inputs to identify what kind of state it is, and then, or I guess maybe I call these state parameters. And then each state has a state value. And in this case, the state value is just the optimized highest possible coins reaching that state. And then there's obviously there's going to be this you need to account for state transitions in code. Like going state transitions in here is like if you're a particular state, if you're a particular row column and you've used the special number of times and you have some neighboring cells in the grid, how do you get to those cells? How do you change to those rows and columns and either maybe decrement the number of specials or not decrement the number of specials, but also track the state value based on that. Okay, so for the dynamic programming, there's going to be a matrix, so a DP matrix, and generally you want to have values for the top number. So it's going to be m and n, so I'll say this is rows and columns is the length of, they call this coins, but this is referred to as grid here. Okay, coins. Length of coins for the number of rows, length of coins at 0 for the number of columns, and it's 3 is the number of, or 2 is the number of uses, right? So 3 possible values for the number of uses, 0, 1, or 2. So it's going to be dp is equal to I think I start with 0. 0 times the number of so the innermost dimension here is I think the coin, so it's multiplied by 3. And then for blank in the range of calls plus 1, and that is done, that is an array for blank in range rows plus 1. Generally you want to have one extra not dimension, but the maximum number of values in a dimension in one of the state parameters is plus 1 when you create the matrix, just because you want to have an initial state which is 0, 0, 0 for those parameters, and then it needs to increment to like the final state, which is like at the very end, which is inclusive of the maximum value of those things. Okay. Neutralize. I don't know if I should use double underscores here. I'm pretty sure it doesn't matter, but so initializing can neutralize up to 2 robbers. Okay, so for every how big is this thing? 500 by 500? Okay. 500 by 500. If you iterate over every possible position, it's 250,000. I'm wondering if I can not iterate over every position. So it's 250,000 plus there's going to be 3 parameters. So, or 3 for the number of uses. Okay, well, let's just give this a whirl. So I need to iterate for every position, I think, here. For every row and range of rows, for every column and range of columns, maybe? Is that right? Sure. So if I'm iterating over like the first row and then all the columns at the first row. Yeah. So I think right now I'm going to go ahead and create a helper method that is valid just to make sure I index into the thing correctly. R index, column index. Return if this is between the number of rows and number of columns. Okay, so a particular row index, do I want to push or do I want to pull? I guess I'll push. I'll push. So at this particular index, so let's say the current is equal to dp rc. This is going to be a 1D matrix of size 3. And actually, maybe I should double check this actually creating it correctly. So it's a 3x3. This doesn't look like it created. No, that's just, yeah, me. 3. So 3x3, each thing should have 3. Yeah, I think that's right. So 4 rows, 4x4, and each thing has a 3 value array. Okay. Okay, so current is equal to that. So the simplest case is if they've used all their robbers or all their special abilities, then they would have to take whatever is the thing at this spot, right? Like they couldn't neutralize anything here. So I can say if use powers twice, must take current. So I think this should be dp of r maybe c plus 1. Actually, do I need to double check is valid for the? So I'm pushing onto the next column based on the current position. dp this row and column 0, 0. Okay, let's go ahead and just say the number of, let's say the spot has coins at RC, right? Okay, so dp of RC plus 1 of 2 is equal to dp of r of c of 2, or I guess this should be just current of 2. Do I need to use maximum? Maximum, what is there in this one? Because I'm pushing that way, but then it could also be, yeah, I think I need to use maximum here because there's 2 directions that the transition could go to for that row and column position. Like it could be from this current row pushing to the right column, or it could be from the previous row pushing down to this column, to this position right here, r c plus 1. So it'll be dp r c plus 1 to current. Okay, and then dp r c plus 1. Okay, and the other thing that could happen is, assuming that there was a robber here, then instead of using the robber, it could be zeroed out. So something like if the spot has a robber, because you would never want to use the power if the spot didn't have a robber. dp of r c plus 1 2. So I'm still using 2 here. I wonder if this should be all chained in here. max of dpr c plus 1 2 and current of 1. So the current position using 1 power, zeroing out whatever the current thing is. Actually, this thing's incorrect, huh? This is supposed to be current using 2 powers plus whatever the spot value is. Okay. Actually, I guess I could always just zero it out. I guess this doesn't have to be checked. I guess maybe I should just use maximum of dp, what's ever there, pushing the current spot or the current number of coins or the robber on the current spot, plus having used 2 powers, or just having used 1 power and applying another power on this spot. Yeah, so something like that. So it doesn't really care that much that it could be a positive value that's zeroing out. Okay. dpr c plus 1 of 1 is equal to max of dpr c plus 1 of 1, current of 0 plus spot, or current of 1, or current of 1 plus spot. No, current of 0. No, current of 1, current of 1. Not applying the power, or applying the power to this thing. And then dp of r c plus 1 of 0 is max of dp of r c plus 1 of 0, and this thing there's no applying the power, so it has to be current of 0 plus whatever is currently here. If you okay, this is the wrong logic here. Next cell 2 powers used. Is best of current at that state. Or transition from 2 used or 1 used, or 1 used at this position. Next cell 1 with 1 power used is best of current. Best of currently there, and or transition. Okay. And likewise for the last one. Okay. I think that's it, to be honest. Actually, whatever's currently there is actually could be 0, right? Which is not, could technically be not possible if you're hiring a bunch of robbers. So I think it, okay, yeah. So this should be negative infinity as the default value. And then the initialization is dp of 0, 0, 0 is equal to 0. So the first cell has 0. Because when you want to do the maximum, you definitely want to improve on the negative infinity to some finite negative, even if it is robbery. I guess if the current position is actually negative infinity, then I just need to skip it because there's, like, if it's at row 0, column 0, and using 1 power or 2 power at that point it's negative infinity, so that's just not a valid thing. So if current, how should I do this? Do I need to do that actually? Not really, right? Because this is just an array. Okay, I think that might be it actually. So return dp of, I guess, the maximum of dp at the last. And this is the array, so it could be that they use 0, 1, or 2 powers. Doesn't make sense to use any number of powers if there's no robbery. There's nothing to have negatives to zero out. So okay, let's see if that works. Oh boy, null. I guess I never use is valid. Wait. No, indeed, huh? Oh yeah, okay. I'm only doing transitioning to the next column. I forgot to do transition to the next row. Fuck. That's so stupid. Okay, transition to next cell below row +1. This is here. This is transition to next cell right. Rightwards column +1. And here I'll say this is for 2 used, either take spot plus or either 0, either use power or take spot, right? Why is this? What? How is that? How is that weird? Okay. And similarly for 1 used, and then for 0 used, there's nothing. There can't be any power used. dp of r plus 1 c2 is equal to max of dp. Yeah, dp of r plus 1 c2 current of 2 plus spot, or current of 1 plus 0. dp of r plus 1 c1 is equal to max of dp of r plus 1 c1 plus or current of 1 plus spot or current of 0, and dp of r plus 1 c0 is equal to max of dp of r plus 1 c0 or current of 0 plus spot. I feel like there could be better ways of having this logic. Yeah, this is still not going to transition correctly. How does it is pushing it to the left and to the bottom. Should... think about this correctly. From a particular cell, it pushes to the left or to the bottom. Maybe I should be transitioning from... So if I'm at the last position at row -1, column -1, then I transition that to the state that is row -1 column. So what's going on here? Yeah, okay, so it is, I think it should be doing like maximum of these set of values, and how's it doing it? It should be, because nothing's gonna end, this thing's always gonna be negative infinity, negative infinity, negative infinity, because transition is from the source moving to the adjacent, rather than from the destination coming from the adjacent sources. So the movement, I think, needs to be, it's kind of arbitrary, right? It should be mirrored, maybe, like 788 and 788. Yeah, this is kind of mirrored. I think that's always what happens. 40, 30, 20, 40, 30, 20. Okay, so I think it just needs to go something like dp of the last column -2, or last row -2 on the column, something like that. Is that gonna work? Yeah, I think that might work. Okay. Cool beans. Although, not particularly fast. Okay. Is there a way for me to shorten this logic? There is a lot of max of values here. I want to say transitioning downwards, you don't have to use max, because there's never an instance where transitioning downwards there was ever a prior value that should have been... No, that's not true. No, that is true. That is true. Like if you transition from a particular row to the cells below it, they're given the iteration of rows and columns, with the outer being rows and inner being column, there shouldn't be... The transition downward should be always first, and there should never be any prior values there that really needs to be maximized across. So I want to say this part is unnecessary. Yeah, I think this part is unnecessary. And so this one doesn't need a max. Okay. I think that logically holds. I mean, it's slightly less. Okay, yeah, it is slightly faster. It is slightly faster. I mean, I guess it's slightly better than slightly. It was like 2500 milliseconds before. So that's like 800 or so, slightly less than 800 milliseconds. So it's like a 33% improvement or so. How to make this better. Current DPRC. I guess I don't need the is valid here. I push right, push right, I push down, push right, push down. Push, push, right, down, right, push, down, push, push, down, push, right. Maximum, go right, 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 right. Don't want to store every possible path. It's not the case that you want to try to just zero out your negatives. Although in theory, yeah, you want to zero out your negatives. Okay, I guess this is it for me for today. Alright, so summary, this is going to be kind of almost kind of canonical kind of dynamic programming type problem. Make sure you define or identify the state parameters. The state parameters, basically the variables that separate or distinguish states. In this case, it'd be the rows, the columns, and the number of specials used, and state value, which in this case is the coins earned up to that state, or the maximum coins earned up to that state. Use a nested for loop, or after creating the dynamic programming matrix, which is to say that you have in this case 3D matrix, because there's 3 state variables, 3 state parameters. 3 parameters. After creating the matrix, use a nested for loop, iterating over the row and column indices, and inside perform logic to transition from the kind of 3 states at that position, basically where it has 0, 1, or 2 used powers, to the neighboring states where you have the where adjacent row or column, right? So either the same row, column plus 1, or the same column, row plus 1, and kind of some similarish or some use powers, right? So either 0, 1, or 2 use powers at that adjacent row or column. And so yeah, so nested for loop, this is the current state. This is a 1D array, has all 3 0, 1, or 2 used powers at this current row. This is the number of coins there, and transition based on that. So for instance, if you have transitioning to the right column where you have used 2 powers at that position, then that means that either you take the current position having used 2 powers plus whatever the coins is at this current position, or you take the current position having used 1 power and basically applying another power, zeroing out the spot coins, basically a robber, hopefully, and not adding that number to whatever the maximum number of coins here is with 1 power. And technically this is maximum because the iteration is going to go rightwards and downwards, and technically downwards is always fresh, but rightwards could be encountering something that was previously created from a downward movement, so therefore it has to take the maximum of what's previously there. Okay. Time complexity, this can be O of mn times 3, so O of mn. Technically, or actually, this is O of mmp, where mn is size of matrix, and or area size of matrix, and p is number of powers used, or maximum number of powers. This one is hard coded as 3, or hard defined as 3 based on the description, but in theory if there was like an arbitrary p-value, a variable p-value, then that'd be it. Since the for loop will iterate over each position in the grid and also iterate over the number of powers. So if there was 4 powers or 4 possible power usage or whatever, then there needs to be 4 in the inner loop. This basically makes this O of M and P. Although in theory this could be reduced to O of NP, I think. NP with some kind of tricks to the storage of state memory. Because in theory, when you do the transition here, it's just like you're doing 1 row at a time, and that row moves to another cell in that same row or to the next row. So you just need to know, if you just had 1D arrays for the single row and the next row, that would be enough. You would need to have prior rows from that, or further rows than that. So yeah.